All right, so let's just get into introduction to GMAT. So I'm going to spend about 20 minutes this morning talking about, what is GMAT, system overview. We'll go over some key features, a little bit of history, where we've come from, where we are now, where we're going, who's participated in GMAT, and how to get further information in the future. So, as the name implies, GMAT stands for General Mission Analysis Tool, and that's what it is. It's a tool for general mission design, analysis of space trajectories. The key characteristics here are, let me draw a little bit, are that it is so high fidelity. So this means that GMAT is not a first guess tool for large trade space analysis. So that's a different application. If you have something, if you're trying to design a constellation just from a goal in your mind, you're not going to jump directly into GMAT. You're going to use a different tool to figure out your trade space and exactly, or to a rough scale, what you're going to do and where you want to go. At that point, you'll take some initial guess states or some concept, you'll put it into GMAT, and you'll simulate your high fidelity trajectory. The goal of GMAT is that it's actually operationally certified, so the numbers that you can get out of this, you can upload directly to a spacecraft. That's the sort of level of fidelity that we're dealing with. Okay. We're going to say it's feature rich. So GMAT tries to contain lots of different features that you might need. It's not something like, well, let's use the constellation example. There are tools specifically designed for constellation design and architectures. This is designed to be applied to any space trajectory application in that high fidelity mode. It is desktop oriented. So this is in contrast with things like GMAS and GMAN and GTDS and things like that are meant to run in batch mode on a mainframe. GMAT is desktop oriented, so this is designed to be used by analysts on their desktop computers at their desks. Okay, that's the use case that we're targeting. And the other two features that are pretty interesting is that it's open source and it's publicly developed. So what makes this different from things like, we'll discuss FreeFlyer and SDK later on and sort of compare and contrast the strengths and weaknesses of both. One of the things that distinguishes GMAT from those tools is that we're open source. Anybody in the world can go and download what we're using right now and use it for whatever application they want to without telling us, without paying us, without signing agreements, nothing like that. And that has benefits internally also because, certain mission operations center or organization can use GMAT without hassles of licensing fees or anything like that. And they can talk to us. This goes into the publicly developed. They can talk to us in sort of a service-based mode instead of a product-based mode where they're paying for a product. They can come to us in a service-oriented fashion, and we can help them develop features that are needed for their application. And with a few minor exceptions, everything we do is publicly developed. We operate in the live public world, so when we're making changes to GMAT, this is how we've operated in the past, and it's a goal to keep doing this in the future. We're coding live, so every commit we make every day is going out to the public. So that's something that we do just to help foster a community. Okay. So as far as system overview, I mentioned some of this stuff, but GMAT is intended for mission analysis and optimization. So optimization is a pretty key factor. We have a whole tutorial on optimization later today. Sorry, can you see through me? All orbital regimes. Okay, so when I say all orbital regimes, we're talking about we've applied it to LEO spacecraft, GEO, lunar, interplanetary, asteroid missions, missions to Mars, libration point, all these orbital regimes. As I said, we're comparable to Astrogator and FreeFlyer in a broad sense. We're both, all three tools are intended for high fidelity mission design, optimization, and analysis. So are we. And in terms of functionality, so I mentioned it's GUI oriented. We have a full-featured graphical user interface, a custom script interface. So we'll go into some of that today. It's cross-platform in the sense that I mentioned a minute ago. So theoretically, GMAT is usable on multiple platforms, although we, limited team size, we can't fully test it on these other platforms internally. But if you had a need for usage of GMAT on other platforms, you could build it on that platform, test it for your own purposes, and use it. I mentioned that we're a precision orbit propagation tool, and we have built-in targeting and optimization, which I'll get to here in a minute. Now, the status of GMAT is that it's fully tested. So I'll mention on the next slide or two how we've gone through a process over the last couple of years of testing GMAT from top to bottom. So everything in there has been rigorously tested and regression tested. Every night we have a test process that goes through and touches every part of the system. So that's what we mean when we say fully tested. And when I say certified for operational use, I'm talking about, maybe I'll get Rizwan to discuss it here in a minute. There's a mission called ACE that we worked with last year to, let's see, you want to just describe what ACE is? And yeah, Rizwan, you want to come up here just for the phone? I'm bringing Rizwan Qureshi up here to talk about what this certified for operational use means.
Hi, so ACE was an Earth-Sun L1 elevation point mission. So GMAT R2013B was selected to be operationally certified. So we selected the ACE mission to go about achieving operational certification using GMAT. So it took about, I think, 6 months of development, internal development, and then now GMAT has been ops qualified to be used in Goddard's flight dynamics facility in the mission operations room to support maneuver planning and operational planning for ACE mission.
Thanks. So that means what I mentioned before, that at least for that use case of a operational L1, Sun Earth L1 mission, we've tested it to the level that the mission agrees the numbers that come out of this could be uploaded to the spacecraft and no undue risk would occur. All right, so this is just sort of a laundry list of features. Just in case you are thinking of something in particular, this might ring a bell as something you might be interested in that we can talk about later. So basic spacecraft models, of course, we have models for state, attitude, mass properties, visualization. For solar system models, SPK and DE files, we can define our own bodies. So user-defined celestial bodies, you can create an asteroid that's not built into GMAT and it'll behave in every way like it was built in. Built-in models for libration points and barycenters. Custom coordinate systems, we have a flexible coordinate system specification environment where you can create your own flexible coordinate systems and they can be used throughout the system. Numerical integrators, we have 8 or 10 numerical integrators you might want to use for different reasons. Force models is a key. I say it's high fidelity. This is where the high fidelity comes in. Of course, third body point mass gravity models, central body non-spherical gravity, atmospheric drag, solar radiation pressure, down to very small effects like Earth tidal forces, solid tides, relativistic effects. The only thing we don't really have here is we don't have a good model for solar SRP over time. So not solar flux over time. So SRP and drag rely on a solar flux number. It measures the incoming radiation from the sun. The limitation here is that you can specify a constant SRP or solar flux value, but you can't input a file that shows how it varies over time and gives predicted values. So that's one weakness here. Otherwise, I think we're in pretty good shape. In terms of ephemeris, you can input in SPK ephemeris and propagate it. So it actually can be used as a post-processing tool. You can simulate your trajectory in another tool, generate a SPK file, a SPICE ephemeris file, import it into GMAT, and then run it out and calculate, export whatever you need. For powered flight, we have thrusters, impulsive burns, finite burns. We'll cover both of those later. Solvers, optimization is a key factor. We do optimization in a much more powerful way than other tools, I think, and we'll cover that later today. But we have functionality in there for both targeting and optimization. BF13, this is the internal optimizer. We also have an interface to MATLAB's fmin-con optimizer. If you have MATLAB, you can use it with GMAT. And then we have programming infrastructure that helps with, you can define a mission entirely in a script language instead of through a GUI interface. And we have built-in programming infrastructure to help define your complex mission. You know, variables, control flow statements. You can call MATLAB functions as if they were GMAT functions. So even though GMAT doesn't have some features built in, if MATLAB has it built in, you can code things up in MATLAB and call them directly from your GMAT script. It's very flexible. Built-in math, and then a calculation parameters subsystem, which I'll cover later today. So in terms of project history, we really got started in 2001. This was before my time, but Steve Hughes in 595 and Dave Folta sort of got together and decided that there are advancements that need to happen in terms of internal mission design tools. Tools like swing-by and things were active, but there needed to be an advance into the Windows environment. So that's how GMAT came to be. 2001, 2000 through 2003 were sort of basic gathering of requirements, building the basic system, and then just ongoing feature development. In 2010, there was a decision, now let's transition GMAT from sort of back-end design work, just everyday design, sort of convenience tool level work, into actual operational use. So that decision was 2010. And we did a bit of feature development just for the next 3 years. 2013A, was our first production release, which is fully tested, fully documented. That's what we say when we call it production, non-beta release. And then 2013 was our operationally certified. So 3 years from decision to our first operational certification. So that's where we are. In terms of public releases, we've had, 3, 4, 5, 6, 7, 8 public releases at this point, dating back to 2007. The most recent one that we're using today is this 2014A. Was finished last month. We just released it to the public on Friday. Last week. I think the folks dialed in on the phone here are the first public users to actually see it. We haven't posted it on a website anywhere, but that's where we are at this point. In terms of participation, well, there's a lot of folks that have participated in GMAT in general. There's government users, so NASA Goddard, of course, leads GMAT. It performs the bulk of the development, of the engineering work, of the project leadership. And I'll mention Thinking Systems and AI Solutions. So Thinking Systems is our primary architectural contractor. So they Daryl Conway at Thinking Systems helped us out with, he actually designed the core system based, back in 2001 and 2003 when the requirements were developed. Steve Hughes and Daryl Conway actually developed the system from the ground up together. And then AI Solutions has been helpful in terms of, in the past several years, in terms of documentation and testing. Tatiana is one of our GMAT testers. And Ann Nicholson is helping out with navigation work. So they have been two contractors that have been intimately related with GMAT development over many years. And then others. So AFRL, JPL, ESA have all contributed features. AFRL started with navigation stuff. JPL did SPICE work. So I'll just write nav, SPICE. And then ESA did some optimization plugins. Now, CARI is the Korean Aerospace Research Institute, South Korean space agency. We've been working with them sort of intimately over the past couple years to develop a variety of features. And then lots of other industry folks that have participated in terms of SBIRs and specific feature development. Here at Goddard, GMAT's seen usage across the spectrum, all the way from LCROSS, which was a lunar impactor mission, up to, it's been used on LRO and OSIRIS and MMS. ACE I mentioned, and more recently, it's the first use of GMAT as a primary design tool is with the TESS mission, which is ongoing right now. And then, of course, future mission studies are all happening all the time, and proposal work, and GMAT's used a lot in that respect. In terms of user base here, so we average, I'm using 13A because 14A is just released last week, but we got about 400 downloads a month from all over the world of GMAT. I think at last count we had more than 30, 35-ish published papers that use results that cited GMAT in their results. That's a sense of scale. Internal to the team right now, we have 14 active members, 6 of which are Goddard, 6 engineers, 7 developers, 1 tester who's sitting in the room right now, and we can say about 450,000 lines of C++ code, 12,000 public commits in our SourceForge repository. I mentioned automated script testing and GUI testing. We have about 11,000 script tests that run every night and touch every part of the system. Another 4,000 automated GUI tests that run about, what is it, Tatiana, every week or so? Every week? Yep. So this is meant to give an impression of the amount of rigor that we put into making sure everything that's in GMAT is correctly functioning. And we have this automated nightly build and test process where we get a new release every night, call it nightly build every night that runs through the testing, and we get results every morning. So in summary, I mean, there's a lot of work that's been done to bring GMAT up from something that is useful to an engineer to something that can be relied upon for mission work. In terms of recent activities, so 13A, I mentioned its first production release, focused entirely on QA and documentation. So very few new features. So we actually didn't do anything with GMAT in terms of putting in new features over the entire year of 2013. It was a full sweep from beginning to end, doing QA and documentation all the way through, and making sure what we had already was up to quality. And actually, we removed features, things that were not up to quality and didn't have the need to be in there. We just removed them entirely and said the system we're going to have is going to be small and lean, and we're going to know it works. That was the goal of 2013A. 2013B was an internal release, specifically for ACE mission operations. We added a few little features for, things that are useful for ops work. Code 500 ephemeris, a reader for initial states, GTDS VHF file reader, a specific coordinate system ACE needed, some new parameters. The real driver for 13B was this operational certification, and so that happened, last summer, last fall?
Yeah.
Yep.
December 2013.
Oh, okay, December, yep. And since then, we've been working on 2014A, which is what you have. It actually includes everything in this 13 release, includes all 13 release features. New stuff from Kari, so we have some new state reps, some new attitude types. So orbit colors, that's handy. A new Mars atmosphere model, some new solver algorithms. These are really, it's really wrapping up some development that's been internal, making it public, and then doing a little bit of mission-specific work for Maven, for TESS, specific missions. So that's what we've done so far, and that's where we are now. In terms of things we're working on in the future, so we really have 3 large-scale features. So number 1 here is event location. So one of the weaknesses of GMAT right now that we'll readily admit is that you cannot simulate your mission and then ask it, what are my eclipse times? When can I see ground stations? What's my maximum eclipse for this duration? You can't do that kind of stuff right now with GMAT. You have to use third-party tools, or you have to code it up in sort of a scripting capability, or send it to SDK and generate eclipse reports. So that's something we're trying to fix. And we're doing that with help from the South Korean Space Agency.
Just one question.
Sure.
You have interface features built into it so that you can output data to another software package?
Yeah, that's a good question. So the question was, do we have features that allow us to export data to another software tool?
Into a file.
Or to a file, right. So the file one we definitely do. So we can export to SPK and CCSDS and Code 500 ephemeris, which is really handy. One of the ways we get around this eclipse limitation is we just export to an ephemeris, load it into SDK, generate our eclipse report that way. You can also, I'll mention the parameter subsystem we have that allows you to query states of your mission. You can print those to a custom report file in text. So there's lots of things you can do to get around this, which is why it's not a killer right now. Another way is you can, I mentioned a MATLAB interface. You can send things directly to MATLAB inside your mission and do whatever you want in MATLAB. One interesting thing we've done is, for Maven, we had a need to show a certain type of plot that GMAT couldn't do internally. So we coded a GMAT function that uses plot commands, and we just run it inside as GMAT's going along. And so it's plotting in a MATLAB window live while GMAT's simulating. It's pretty powerful. Another thing, number 2, that would make that a lot better is if we had native GMAT functions. So we have a nice scripting language, but you can't write native functions in GMAT's own scripting language, which is hugely important for any kind of reusability. So that's something we're working on. And then 3, we have low thrust development. So GMAT can do low thrust in sort of a naive general finite burn model sort of way. It is not set up right now to be able to design low thrust missions from scratch, and you have to do things like multi-segment trajectories with tens to hundreds to thousands of segments and use tools like optimal control methods, and that's the sort of thing we're talking about when we say low thrust development. Also included in that is specific models for electric engines and nuclear engines and related hardware. All right, so mission specific development. I mentioned we're working with tests right now. We have worked with Maven, and Rizwan back there is working with JWST mission just to see if we can help them out on any particular needs. And then navigation subsystem. We have work that we've done with AFRL to do a baseline navigation component. We're talking about measurement models and filters and estimators. So we're in a process right now of redesigning this and making it more production level instead of an alpha level subsystem. All right, so I'll just touch on this briefly. I'll cover it at the end also, but our main website is GMAT Central. We have some user forums, some documentation. We have a public bug tracker. You can see all of we air our dirty laundry in terms of public development. So you can actually go in there and see we have, 2,000 open issues and feature requests and status of all of our bugs and things like that. And when I say public development, it's really nice because you can, if you have a bug, you can just go in there and submit it, and you can comment on it and upload your scripts. It helps us out. In terms of getting involved, this is sort of a new thing I'm emphasizing this time, but if you, at the end of this class, if you think, well, GMAT's a really cool project, I wish I could do X or Y, or I just want to get involved in it, how can you do that? Well, the most basic thing you can do is we have forums and mailing lists, and you can, people ask us questions, and one easy way to get involved is just to answer people's questions, or try to write up scripts that solve certain problems, post it to the forum, help other people out. The next level is you can submit bugs. So if you have bugs and feature requests that you can submit those directly to Jira. We'll look at them every week, prioritize them, and fix the ones that are high priority. We have some pretty solid documentation this release, which is a change from years past. 700 pages of full documentation on every part of GMAT. But, documentation is always helpful. It can always be improved, and this is sort of an easy place to get started. And then if you're a coder, you could help us actually fix bugs. You can contribute to feature requests, or at the most important thing, and really the hardest thing is if you have a feature request, coding up and contributing entire new features. So this is sort of the spectrum of ways to get involved. So that's really it in terms of overview to the GMAT project. At this point, we're going to switch gears and talk about, well, we're going to stop talking, essentially. We're going to actually open GMAT and start using it on a tutorial and poke some buttons and things. Any questions at this point about the project?